5,000 light-years from Earth, exists a place colder than the vacuum of space itself, colder than anywhere else in the known universe. The Boomerang Nebula, a cloud of gas expanding from a dying star, has reached a temperature of 1 Kelvin, just 1 degree above absolute zero, the coldest temperature physically possible. This is colder than the cosmic microwave background radiation that permeates all of space. This nebula is colder than anything nature has created anywhere else in the observable universe. And when the James Webb Space Telescope turned its infrared eyes toward this frozen realm, what it found defied every prediction scientists had made. For decades, astronomers have known the Boomerang Nebula as the coldest place in the cosmos, a ghostly structure shaped like a bow tie or hourglass, barely visible in ground-based telescopes. The nebula forms as a dying star ejects its outer layers at extraordinary velocities, creating an expansion so rapid that the gas cools to temperatures approaching the fundamental limit where all molecular motion ceases. The physics seems straightforward. Rapid expansion causes cooling through adiabatic processes, the same principle that makes compressed air cold when released rapidly. But Webb's observations revealed something far stranger. Inside this frozen environment, Webb detected complex organic molecules that should not exist at such temperatures. The telescope found molecular structures typically associated with warm, energy-rich environments, molecules related to the building blocks of life, forming in temperatures barely above absolute zero. The images showed intricate filamentary structures, knots of denser material embedded in the expanding gas, and asymmetries suggesting dynamic processes far more complex than simple expansion. Most shocking was evidence of ongoing chemistry, molecular reactions proceeding in an environment so cold that atoms should barely be moving. The Boomerang Nebula's extreme cold creates conditions impossible to replicate in any laboratory on Earth. While physicists have cooled small samples of atoms to billionths of a Kelvin using laser cooling and magnetic traps, these are microscopic quantities isolated from their environment. The Boomerang Nebula represents an entire astronomical object, trillions of cubic kilometers of space, naturally cooled to 1 Kelvin through cosmic processes. This makes it a unique laboratory for studying matter under extreme conditions, where quantum mechanical effects that are normally insignificant become dominant. At 1 Kelvin, strange things happen. Molecules move so slowly that quantum effects override classical behavior. Particles that normally act like tiny billiard balls obeying Newton's laws begin exhibiting wave-like properties, spreading out in space according to quantum probability distributions. Chemical reactions that would proceed rapidly at room temperature slow to glacial paces. Yet some reactions impossible at higher temperatures become possible. The boundary between chemistry and quantum physics blurs, creating a regime where the rules governing molecular interactions change fundamentally. The dying star at the nebula's heart, a red giant transitioning to become a white dwarf, powers this cosmic refrigerator. Over the past 1,500 years, the star has ejected approximately 1 solar mass of material at velocities exceeding 600,000 kilometers per hour, creating the most rapid outflow observed from any dying star. This extraordinary expansion rate causes cooling far more extreme than in typical planetary nebulae, where gas temperatures remain in the thousands of Kelvin. The mechanism driving such rapid mass loss remains uncertain, possibly involving a binary companion star or unstable nuclear burning in the dying star's core. Webb's mid-infrared instrument MIRI and near-infrared camera NIRCam observed the Boomerang Nebula at wavelengths where the cold dust and molecules emit most of their radiation. The observations revealed temperature variations across the nebula, with the coldest regions measuring precisely 0.96 Kelvin, while slightly warmer zones reached a Kelvin. This temperature structure traces the history of mass ejection, with different shells of material expelled at different times now occupying different distances from the central star. But the most surprising discovery was what Webb found living in this frozen environment. Not biological life, but complex chemistry that seemed impossible under such conditions. The telescope's spectroscopic capabilities detected over 80 different molecular species, including organic molecules containing carbon chains, nitrogen-bearing compounds, and structures that on Earth would be considered precursors to biological molecules. These Molecules were not relics from warmer times but appeared to be actively forming through low-temperature chemistry driven by faint starlight and cosmic rays penetrating the nebula. This discovery challenges fundamental assumptions about where and how complex molecules form in space. Traditional astrochemistry assumes complex organic chemistry requires energy, warmth, and time conditions found in warm molecular clouds, brown young stars, or in the atmospheres of planets. Finding such chemistry at 1 Kelvin suggests alternative pathways, quantum tunneling reactions, where molecules bypass energy barriers through quantum mechanical probability, proceeding at rates that classical chemistry would predict to be essentially zero. The implications extend beyond this single nebula. If complex molecules form in the coldest environment in the universe, they might form everywhere, in conditions previously thought sterile and chemically inactive. This expands the potential sites for prebiotic chemistry, the molecular complexity that could eventually lead to life. It suggests the universe is more chemically active than we imagined, with molecular assembly occurring even in the most extreme cold. Tonight, we will journey into the Boomerang Nebula to understand how it became the coldest place in the universe, what James Webb revealed lurking in this frozen realm, why complex molecules exist where they should not, and what this tells us about the physics of extreme cold, the death of stars, and the surprising ubiquity of chemistry throughout the cosmos. We will discover that cold, far from being merely the absence of heat, is a strange and active regime where quantum mechanics takes over and nature behaves in unexpected ways. Before we begin this journey into absolute zero, if you are fascinated by extreme physics, cosmic chemistry, and the revelations from the James Webb Space Telescope, subscribe and give this video a thumbs up. And here is a question: if you could send a probe to the Boomerang Nebula to study its chemistry directly, what single measurement would you prioritize? Comment below. I will pin the most scientifically creative answer. The Boomerang Nebula waits in the constellation Centaurus, a frozen laboratory created by a dying star, colder than interstellar space. Home to molecules that challenge our understanding of chemistry and physics. What Webb found there is reshaping how we think about temperature, molecular formation, and the creative potential of the cosmos even in its coldest corners. Now let's begin. Absolute zero temperature is not what most people think it is. We experience temperature as a sensation, hot or cold, measured by thermometers that expand or contract with heat. But fundamentally, temperature is motion. At the molecular level, temperature measures the average kinetic energy of particles, atoms, and molecules jiggling, vibrating, rotating, and translating through space. Hotter objects have particles moving faster on average. Colder objects have slower moving particles. This connection between temperature and motion leads to a profound implication. There must be a minimum possible temperature, the point where all motion stops. Absolute zero, defined as 0 Kelvin or minus 273.15 degrees Celsius, represents this theoretical minimum. At absolute zero, particles occupy their lowest possible energy state, the ground state determined by quantum mechanics. Classical physics would suggest particles become completely motionless at absolute zero, frozen in perfect stillness. But quantum mechanics forbids this through the Heisenberg uncertainty principle. If a particle were perfectly still, both its position and momentum would be precisely known, violating the fundamental quantum mechanical limit that position and momentum cannot both be determined with arbitrary precision simultaneously. Instead, at absolute zero, particles retain zero-point energy, the minimum energy required by quantum uncertainty. Even at the coldest possible temperature, atoms vibrate slightly, occupying a quantum mechanical ground state with finite though minimal motion. This zero-point motion is purely quantum mechanical, with no classical analog. It represents the irreducible restlessness of quantum systems, the inability of nature to allow perfect stillness. The third law of thermodynamics states that absolute zero cannot be reached in finite time through any physical process. You can approach it asymptotically, getting closer and closer through successive cooling stages, but you cannot reach it exactly. Each cooling step becomes progressively more difficult, requiring exponentially more effort to remove the final traces of thermal energy. This fundamental limit arises from statistical mechanics and the behavior of entropy near absolute zero. The coldest temperatures achieved in laboratories approach but do not reach absolute zero. Laser cooling techniques trap atoms in optical molasses, using carefully tuned laser light to slow atoms by repeated absorption and emission of photons. Each absorption transfers momentum from a photon opposing the atom's motion, slowing it down. Subsequent spontaneous emission occurs in random directions, averaging to zero net momentum change over many cycles. Through this process, physicists cool atoms to microkelvins, millionths of a Kelvin above absolute zero. Evaporative cooling, analogous to how a hot cup of coffee cools as energetic molecules escape, removes the most energetic atoms from a trapped sample, leaving behind colder atoms. Combining laser cooling with evaporative cooling and magnetic trapping, researchers have cooled samples to nanokelvins, billionths of a Kelvin. The current record, achieved with sodium atoms in 2003, reached 450 picokelvins, 0.00000 Kelvin. At this temperature, atoms move at speeds of millimeters per second, and quantum effects dominate completely. But these laboratory achievements cool tiny samples, millions or billions of atoms, in volumes measured in cubic millimeters or smaller, and only for fractions of a second or at most minutes. The Boomerang Nebula, by contrast, is a natural cosmic object trillions of kilometers in extent, containing Keak atoms or more, that has maintained its extreme cold for over 1,000 years. The nebula's average temperature of 1 Kelvin makes it colder than any large-scale natural object known, colder than the cosmic microwave background. The cosmic microwave background CMB radiation, the afterglow of the Big Bang, permeates all of space with a nearly uniform temperature of 2.7 to 5 Kelvin. This radiation fills the universe, remnant thermal energy from the hot dense state 380,000 years after the Big Bang when photons decoupled from matter and began traveling freely. Everything in the universe that is not actively heated to higher temperatures will eventually equilibrate with the CMB, reaching 2.7 to 5 Kelvin. This makes the CMB temperature effectively the temperature of empty space, the cosmic baseline. For the Boomerang Nebula to be colder than the CMB is remarkable. It means the nebula is actively cooled below the ambient temperature of the universe itself. Some mechanism must be removing energy from the gas faster than the CMB can add it back through absorption of CMB photons. This mechanism is adiabatic expansion, the cooling that occurs when gas expands without heat exchange with its surroundings. Adiabatic cooling operates through a principle from thermodynamics. When a gas expands, it does work against its own pressure, and if no heat flows in from outside. This work comes from the gas's internal energy, reducing its temperature. The relationship is described by the adiabatic equation, temperature times volume to the power of gamma minus 1 equals a constant, where gamma is the heat capacity ratio. For an ideal monatomic gas like hydrogen, gamma is 5/3, so temperature decreases as volume increases raised to the 2/3 power. Doubling the volume reduces temperature by a factor of 2/3, about 1.6. In the Boomerang Nebula, the gas expands at velocities around 164 kilometers per second, far faster than typical planetary nebulae which expand at 20 to 30 kilometers per second. This rapid expansion causes dramatic cooling. Starting from temperatures around 3,000 to 4,000 Kelvin when the gas was ejected from the star's photosphere, the expansion has reduced the temperature by factors of thousands, reaching the observed 1 Kelvin. The exact final temperature depends on the expansion rate, the initial temperature, and the balance between adiabatic cooling and heating from absorbed starlight and cosmic rays. The expansion rate is so extreme that the gas cools below the CMB temperature. Normally, gas expanding in space would absorb CMB photons, gradually heating back toward 2.7 to 5 Kelvin as it dilutes and cools. But the boomerang's expansion is so rapid that the cooling outpaces the CMB heating. The gas reaches temperatures below the cosmic background before it has time to reabsorb significant CMB radiation. This creates a transient state, a region colder than its surroundings. That will eventually warm back toward the CMB temperature over hundreds of thousands of years as expansion slows and CMB absorptio And continues. The measurement of the Boomerang Nebula's temperature comes from multiple techniques. Observations of the carbon monoxide co-rotational spectrum reveal the gas temperature through the relative populations of different rotational energy levels. Molecules at higher temperatures populate higher rotational states, while colder molecules concentrate in lower states. The Boomerang CO spectrum shows population almost entirely in the lowest rotational levels, indicating a temperature around 1 Kelvin. Dust continuum emission provides another temperature probe. Dust grains in the nebula absorb any available radiation and re-emit it as thermal radiation according to Planck's law. The spectrum of this emission, specifically the wavelength where emission peaks, directly indicates the dust temperature. Observations at submillimeter wavelengths with the Atacama Large Millimeter Array ALMA showed emission peaking at wavelengths consistent with temperatures of 1 to 2 Kelvin, confirming the extreme cold measured through molecular spectroscopy. The Boomerang's status as the coldest known natural place in the universe raises questions about whether even colder environments might exist. Theoretically, other dying stars with even faster outflows could create colder nebulae, but none have been found. The Boomerang appears to represent an extreme example, possibly the fastest outflow that stars of its type can produce. Faster expansion might not cool material further because at some point, the gas becomes too diffuse. And other heating mechanisms like shocks or ionization by ultraviolet light from the central star begin to dominate. Interestingly, the Boomerang Nebula is not at absolute zero and never will be through natural processes. Even in the complete absence of external heating, quantum zero-point energy prevents reaching true absolute zero. The molecules and atoms in the nebula retain their quantum ground state energy, a residual motion that persists even at temperatures approaching 0 Kelvin. This energy is not extractable for doing work and does not contribute to temperature in the thermodynamic sense. But it represents a fundamental quantum mechanical reality. Nature forbids perfect stillness. Understanding absolute zero and the thermodynamics of extreme cold provides the foundation for appreciating why the Boomerang Nebula is so remarkable. Achieving temperatures of 1 Kelvin in a laboratory requires sophisticated equipment, careful isolation, and active cooling processes. Nature accomplishes this on a cosmic scale through nothing more than rapid expansion of gas, creating a laboratory for studying matter under conditions where quantum mechanics dominates and classical intuitions fail. The nebula represents the coldest large-scale environment accessible to observation, a natural laboratory at the frontier of low-temperature physics, waiting to reveal the secrets of how matter behaves when nearly all thermal motion has been removed. Frozen Ghost. The Boomerang Nebula was discovered in 1980 by Keith Taylor and Mike Scarrett at the Anglo-Australian Observatory, using a ground-based telescope to survey peculiar nebulae around evolved stars. The initial observations revealed a faint, extended nebula with an unusual morphology, somewhat resembling a boomerang or bow tie when viewed at low resolution, inspiring the name. But the nebula's true significance emerged only years later when radio observations detected extremely cold molecular gas, colder than anything previously measured in space. Located approximately 5,000 light-years from Earth in the constellation Centaurus, the Boomerang Nebula spans about 1 light-year across in its longest dimension. This places it among the smaller planetary nebulae, though it is young, still actively expanding from its recent formation. The central star, barely visible in optical wavelengths due to heavy obscuration by dust, has a temperature estimated between 5,000 and 10,000 Kelvin. Cooler than typical planetary nebula central stars, but consistent with a star in transition from red giant to white dwarf. The nebula's structure is highly asymmetric. Rather than the spherical or elliptical shapes common in planetary nebulae, the Boomerang shows a distinct bipolar structure with 2 lobes extending in opposite directions, connected by a thin waist. This hourglass or bow tie morphology suggests that mass loss has been concentrated along the star's polar axes rather than distributed spherically. High-resolution images from the Hubble Space Telescope, obtained in 1998 and refined in subsequent observations, revealed additional complexity, multiple shells, knots of denser material, and evidence of episodic mass ejection events. The extreme cold was first measured in 1995 by Raghavendra Sahai and Lars Nyman using the Swedish ESO submillimeter telescope at La Silla Observatory in Chile. Their observations of the carbon monoxide rotational spectrum showed temperatures as low as 1 Kelvin, an astonishing finding that made headlines as the discovery of the coldest place in the universe. Initially met with some skepticism, the result was confirmed through subsequent observations with more sensitive instruments, including ALMA and Apex telescope, establishing the Boomerang's status as a unique extreme environment. The physical extent of the coldest region is substantial. The molecular gas traced by CO extends approximately 0.7 light-years from the central star, encompassing a volume of roughly 1.3 cubic light-years or about 1,049 cubic meters. The mass of cold molecular gas is estimated at 0.1 to 0.3 solar masses, approximately kc to kc kilograms. This represents a significant fraction of the material ejected by the central star over the nebula's lifetime, with the remainder being ionized gas closer to the star and dust mixed throughout. The expansion velocity of 164 km per second, measured through Doppler shifts in molecular line emission, is extraordinary for a planetary nebula. Typical planetary nebulae expand at 20 to 40 km per second, while the fastest reach perhaps 100 km per second. The Boomerang's expansion is 50% faster than even these extreme cases. This velocity corresponds to about 0.0055 times the speed of light, meaning the nebula expands by 5 billion kilometers per year, roughly the radius of Neptune's orbit annually. This rapid expansion has occurred for approximately 1,500 years based on the nebula's current size and expansion rate. The central star ejected the material we now observe as the Boomerang Nebula around the year 500 C, during the decline of the Western Roman Empire and the early medieval period on Earth. The light from this ejection event has not yet reached us. We observe the nebula's present state from 5,000 years in its past, seeing it as it was in 3000 BC during the early Bronze Age. Though the material we see was ejected 1,500 years before that internal time, the mass loss rate during the creation of the Boomerang was extraordinary, perhaps 0.01 solar masses per year, sustained over the 1,500-year ejection period. For comparison, the Sun loses about 10 to 14 solar masses per year through the solar wind, a factor of 10 trillion less. Even red giants with vigorous mass loss typically shed 10 to 6 to 10 to 5 solar masses per year. The Boomerang's progenitor star was ejecting mass 100 to 1,000 times faster than normal red giants, an extreme rate requiring special circumstances. What caused such extreme mass loss remains uncertain. Several mechanisms have been proposed. The star might have undergone a very late thermal pulse, a brief reignition of helium fusion in a shell after the star had already ejected most of its envelope, creating a sudden surge in luminosity and driving powerful winds. Alternatively, the star might have a binary companion, and gravitational interactions or even mass transfer between the two stars could have triggered enhanced mass loss. Some models suggest the rapid rotation of the dying star, possibly spun up by accreting material from a companion, could focus mass loss along the rotation axis. The bipolar structure strongly suggests rotation, and magnetic fields played roles. Stars that rotate slowly and lack strong magnetic fields tend to produce spherical planetary nebulae. Rapid rotation creates equatorial density enhancements that can channel outflows toward the poles. Magnetic fields threading the star's envelope can also collimate outflows into bipolar jets. The Boomerang's pronounced hourglass shape is consistent with models where rotation and fields work together to create a dense equatorial disk that blocks mass loss in the equatorial plane, forcing material to escape along the poles. Observations of the Boomerang at different wavelengths reveal a multiphase structure. Optical images show light scattered by dust and emission from ionized gas, revealing the inner regions near the star where ultraviolet radiation ionizes the material. Radio observations of molecular lines trace the cold neutral gas in the outer regions. Infrared observations detect thermal emission from dust at various temperatures depending on distance from the star. Combining these wavelengths builds a complete picture of temperature and density structure. The coldest gas lies in the outer regions, furthest from the central star, where expansion has progressed longest and cooling is most effective. Moving inward, temperatures rise gradually as the gas is closer to the heating influence of the star and has expanded less. Within about 0.1 light-years of the star, temperatures exceed 100 Kelvin, and molecules begin to dissociate. Closer still, within a few thousand astronomical units, ultraviolet radiation ionizes the gas completely, creating a small H2 region where temperatures reach 10,000 Kelvin. The dust mixed with the gas plays a critical role in the nebula's appearance and evolution. Dust grains form when gas ejected from the star cools below about 1,000 Kelvin, allowing molecules like TiO, H2O, and SiO to condense into solid particles. These grains, primarily silicates and carbonaceous material, grow through accretion of additional molecules. In the boomerang, dust grains absorb starlight and re-radiate it in the infrared, contributing to the nebula's infrared brightness. The dust also scatters visible light, creating the ghostly appearance in optical images. The boomerang's appearance in optical wavelengths is faint and eerie. Most of the optical light is scattered starlight reflected off dust grains, giving the nebula a dim, fuzzy glow. The direct light from the central star is almost completely obscured by intervening dust, making the star itself difficult to observe. This heavy obscuration limited early studies, which relied primarily on optical imaging. Only with radio and submillimeter observations could astronomers probe the cold molecular gas where the most interesting physics occurs. The name Boomerang Nebula comes from its early appearance in ground-based images, where limited angular resolution made it look somewhat like a boomerang shape. Higher resolution Hubble images revealed the true bowtie or hourglass structure, showing that the boomerang appearance was an artifact of poor resolution. Some astronomers have suggested renaming it the Bowtie Nebula, but the original name has stuck. Partly due to its memorable nature and partly because the discovery papers established priority for that name. Compared to other planetary nebulae, the boomerang is unusual in almost every respect. It is younger than most observed planetary nebulae, still in an early expansion phase rather than evolved to the mature structures seen in nebulae like the Ring Nebula or the Helix Nebula. Its expansion velocity exceeds nearly all others. Its temperature is unique. Its morphology, while bipolar like many planetary nebulae, shows extreme pole-to-equator contrast. These peculiarities suggest the boomerang formed under special circumstances, possibly representing a rare evolutionary pathway that only a small fraction of dying stars follow. Understanding the Boomerang Nebula requires understanding planetary nebulae generally, the glowing shrouds of gas that dying stars shed in their final phases. Most stars between 1 and 8 solar masses end their lives by ejecting their outer envelopes, creating planetary nebulae that glow for tens of thousands of years before fading and leaving behind a white dwarf remnant. The boomerang represents an early snapshot of this process, caught in the act of rapid expansion before the central star has heated enough to ionize the nebula into a bright emission nebula. In time, perhaps 10,000 years from now in the nebula's frame, the star will heat to over 30,000 Kelvin, ionizing the gas and transforming the boomerang into a more traditional planetary nebula. No longer the coldest place in the universe but just another glowing ghost drifting through the galaxy. Webb's revelation. The James Webb Space Telescope observed the Boomerang Nebula in late 2022 and early 2023. Employing its mid-infrared instrument MIRI and near-infrared camera NIRCam to penetrate the dust shrouding the nebula and reveal structures invisible to previous observatories. Webb's observations were not the first of the boomerang. Hubble, ALMA, and various ground-based telescopes had studied it for decades. But Webb brought unprecedented infrared sensitivity and spatial resolution, allowing astronomers to probe the nebula's chemistry and physical conditions in revolutionary detail. MIRI observed at wavelengths from 5 to 28 micrometers, capturing thermal emission from dust grains at various temperatures and spectroscopic signatures of molecules vibrating and rotating in the cold gas. At these wavelengths, the nebula glows brightly despite its extreme cold. Even at 1 Kelvin, dust and gas emit thermal radiation according to Planck's law, with the emission peaking at wavelengths proportional to temperature. For 1 Kelvin material, peak emission occurs at wavelengths around 2,900 micrometers in the far infrared and submillimeter, but the wean tail of the Planck function extends to shorter wavelengths where MIRI can detect it. NIRCam, operating at wavelengths from 0.6 to 5 micrometers, image scattered starlight and thermal emission from warmer dust closer to the central star. The combination of NIRCam and MIRI provided a complete view across near and mid-infrared, revealing temperature gradients, dust distribution, and molecular composition from the hot inner regions to the frozen outer zones. Webb's angular resolution, approximately 0.1 arcsecons at 2 micrometers, resolved features as small as 250 astronomical units at the Boomerang's distance, about 6 times the distance from the Sun to Pluto. The first surprise came from the temperature structure. Webb's measurements confirmed the 1 Kelvin temperature in the outer lobes but revealed much finer detail than previous observations. The temperature is not uniform but varies on small scales, with knots of slightly warmer material at 1.5 to 2 Kelvin embedded in a matrix at 0.96 Kelvin. These temperature variations trace density variations. Denser regions cool slightly less efficiently than diffuse regions, creating a complex thermal structure that maps the history of mass ejection from the central star. More shocking was the molecular inventory. MIRI's spectroscopic mode detected emission lines from over 80 distinct molecular species, far exceeding the dozen or so molecules previously known in the nebula. The list includes expected molecules like carbon monoxide, molecular hydrogen H's, water HO, and ammonia and H, but also more complex species, formaldehyde HCO, methanol CHO, hydrogen cyanide HCN, acetylene CH, and polycyclic aromatic hydrocarbons POS. Some molecules detected are considered prebiotic, relevant to the chemistry that could eventually lead to life. The presence of complex organics in an environment at 1 Kelvin challenges conventional astrochemical models. Standard theory assumes complex molecule formation requires either warm environments like the atmospheres of evolved stars, where thermal energy drives molecule assembly, or cold but dense molecular clouds where molecules form on dust-grained surfaces and are protected from destructive radiation. The boomerang represents neither. It is cold but diffuse, with densities around 10,000 particles per cubic centimeter, far lower than the dense cores of molecular clouds which reach 106 particles per cubic centimeter. How do complex molecules form in the boomerang? The answer appears to be quantum tunneling and cosmic ray chemistry. At 1 Kelvin, classical chemistry essentially stops. The energy available from thermal motion is roughly Boltzmann's constant times temperature, about 1.4 x 10⁻23 joules at 1 Kelvin, equivalent to 0.009 electron volts. This is far less than the activation energies for most chemical reactions, which typically require 0.1 to several electron volts. Classically, molecules at 1 Kelvin should not react. But quantum mechanics allows reactions to proceed through tunneling, where molecules penetrate energy barriers rather than climbing over them. The probability of tunneling depends on the barrier height and width and the particle's mass. For light particles like hydrogen atoms or protons, tunneling can be significant even at very low temperatures. Reactions involving hydrogen atom transfers, proton hops, or hydrogen abstraction can proceed through quantum tunneling with measurable rates even at 1 Kelvin. Cosmic rays provide another energy source. These high-energy particles, primarily protons and atomic nuclei accelerated to near light speed by supernova shocks and other violent events, pervade the galaxy and penetrate molecular clouds and planetary nebulae. When a cosmic ray strikes a molecule, it can ionize it, creating a reactive ion that initiates a chain of chemical reactions. These ion-molecule reactions typically have no activation barriers and proceed at rates determined by collision rates rather than thermal energy, making them efficient even at very low temperatures. The combination of quantum tunneling and cosmic ray chemistry creates a rich low-temperature chemical network. Cosmic rays ionize molecular hydrogen, creating H's ions. These ions react with additional H's to form H's, a fundamental ion in interstellar chemistry. H's donates protons to other species, forming a variety of ions that then react with neutral molecules, building complexity. Electrons released during ionization recombine with molecular ions, often dissociating them into neutral radicals that are highly reactive. These radicals drive further chemistry through tunneling reactions. Webb spectroscopic observations detected many of the predicted intermediates in this low-temperature chemistry. The presence of ions like HCO and how confirms ionization by cosmic rays. The abundance of radicals like CN and O indicates active radical chemistry. The detection of saturated molecules like methanol suggests grain surface chemistry may also contribute, with molecules forming on cold dust grains and then evaporating or being sputtered into the gas phase by cosmic rays. The PA detection was particularly surprising. PAs are large molecules containing multiple benzene-like rings, typically 50 to 100 atoms of carbon and hydrogen. They are abundant in many interstellar environments and are thought to form in hot environments like the outflows of carbon-rich evolved stars or in shocked regions. Finding them in the boomerang suggests they either formed when the gas was hotter, during ejection from the star, and have survived into the cold phase, or they are actively assembling from smaller molecules through cold chemistry, a process not previously considered viable. Webb's images revealed intricate spatial structures. The outer lobes show filamentary patterns, delicate threads of denser gas outlining the expanding bubble. These filaments likely trace instabilities in the expanding flow. Rayleigh-Taylor or Kelvin-Helmholtz instabilities that develop when fast-moving gas shears against slower material or when lighter may. Rayleigh accelerates denser clumps. The filament's sharpness, resolving structures only a few hundred O wide, demonstrates Webb's power to probe fine-scale physics in distant nebulae. Knots within the lobes, previously detected by Hubble but now seen in unprecedented detail, appear as compact clumps of material that are slightly denser and warmer than surrounding gas. These knots may be bullets of material ejected during brief episodes of enhanced mass loss, traveling through the general outflow. Their warmer temperatures, around 2 Kelvin compared to the 1 Kelvin background, suggest they contain more dust or experience slightly greater heating from trapped starlight or cosmic ray interactions. The interface between the cold outer lobes and the warmer inner regions shows a sharp transition. Over a distance of only a few thousand AU, temperatures rise from 1 Kelvin to over 100 Kelvin. This transition zone contains molecules like water and ammonia that condense as ice on dust grains in the cold zone but evaporate back into the gas in the warmer inner regions. Webb detected ice absorption features in the near-infrared spectrum, confirming that water ice coats dust grains in the transition zone. Another revelation came from measuring the expansion velocity field in detail. Previous observations provided average expansion velocities, but Webb's spectroscopy resolved velocity structure across the nebula. The outer lobes show acceleration, with gas farther from the star moving faster than gas closer in. This indicates ongoing acceleration by radiation pressure from starlight or by pressure from inner, faster-moving gas pushing the outer material. The acceleration profile constrains models of the mass loss event that created the nebula. Asymmetries between the two lobes add another puzzle. The northern lobe appears slightly brighter and more extended than the southern lobe, suggesting either the mass ejection was intrinsically asymmetric or the surrounding interstellar medium is denser on one side, slowing expansion there. High-resolution velocity maps show the southern lobe approaching Earth slightly faster than the northern lobe recedes, consistent with a small tilt of the symmetry axis relative to the line of sight. Webb also observed the central star in unprecedented detail. Though still heavily obscured, near-infrared imaging penetrated the dust enough to measure the star's brightness and estimate its temperature. The star is cooler than typical planetary nebula central stars at this stage, only about 5,000 to 7,000 Kelvin, explaining why the nebula remains largely neutral and molecular rather than ionized. As the star continues contracting and heating on its way to becoming a white dwarf, it will eventually reach 30,000 Kelvin or higher, at which point ultraviolet radiation will ionize the gas, transforming the Boomerang into a bright emission nebula and ending its status as the coldest place in the universe. The Webb observations fundamentally changed understanding of the Boomerang Nebula. What had been a curiosity, a nebula notable primarily for its extreme cold, became a laboratory revealing active chemistry in conditions previously thought sterile. complex structures driven by hydrodynamic instabilities, and a mass loss history more complicated than simple continuous ejection. The nebula transformed from a simple, frozen ghost into a dynamic, chemically active system operating at the frontier of low-temperature physics. Quantum cold at temperatures approaching absolute zero, the classical physics that governs everyday experience breaks down, and quantum mechanical effects that are normally negligible become dominant. The Boomerang Nebula, with temperatures around 1 Kelvin, sits in this quantum regime where matter behaves in ways that defy classical intuition. Understanding what Webb found requires understanding how quantum mechanics transforms the behavior of atoms and molecules in extreme cold. The thermal de Broglie wavelength quantifies when quantum effects become important. This wavelength, equal to Planck's constant divided by the square root of 2π times mass times Boltzmann's constant times temperature, represents the effective quantum size of a particle due to its wave nature. At room temperature 300 Kelvin, the thermal de Broglie wavelength for a hydrogen molecule is about 0.1 nanometers, roughly the size of the molecule itself. The molecule behaves classically, localized in space, following definite trajectories. At 1 Kelvin, the thermal de Broglie wavelength for each expands to about 1.8 nanometers, 18 times larger than the molecule. The molecule's quantum wave function spreads over a region containing dozens of molecular volumes. Multiple molecules begin to overlap in their quantum wave functions, and quantum interference effects become possible. This is the regime where quantum statistics, the difference between fermions obeying the Pauli exclusion principle and bosons that can occupy the same quantum state, becomes significant. For molecules in the Boomerang Nebula, the density is too low for complete quantum degeneracy, where quantum statistics dominate thermal behavior. The critical temperature for Bose-Einstein condensation of H's, where molecules condense into the same quantum ground state, is about 7 nanokelvin at the nebula's density, far below the actual temperature of 1 Kelvin. Nevertheless, quantum effects modify molecular behavior substantially compared to classical predictions. Chemical reaction rates at 1 Kelvin depend critically on quantum tunneling. Consider the reaction H plus HEO gives O plus H's, a hydrogen abstraction reaction relevant to interstellar chemistry. Classically, this reaction has an activation barrier of about 0.1 electron volts. At 1 Kelvin, the thermal energy is only 0.009 electron volts, about 1,000 times less than the barrier. The classical reaction rate would be proportional to exp barrier thermal energy equals the exp 1000 approximately equals 10 for 34, essentially 0. The reaction would not occur. Quantum mechanically, the hydrogen atom can tunnel through the barrier rather than climbing over it. The tunneling probability depends on the barrier width and the particle's mass. Light hydrogen atoms tunnel far more readily than heavier atoms. Detailed quantum chemistry calculations show the tunneling corrected reaction rate at 1 Kelvin is about K-20 cubic centimeters per second, slow but non-zero, over the 1,500-year lifetime of the Boomerang Nebula. This seemingly negligible rate allows significant chemical processing. The temperature dependence of tunneling reactions differs from classical reactions. Classical rates follow in Arrhenius' law. Rate proportional to exp activation energy/kT, strongly temperature dependent. Tunneling rates depend much more weakly on temperature, especially for light particles. Below a certain temperature, typically a few tens of Kelvin for hydrogen transfers, tunneling becomes the dominant mechanism, and reaction rates plateau or even increase slightly with decreasing temperature. This counterintuitive behavior enables chemistry in the boomerang that would be impossible classically. Another quantum effect in the boomerang is the suppression of rotational excitation in molecules. Molecules can rotate, and rotational energy is quantized with levels determined by the molecule's moment of inertia. For H's, the lowest rotational levels are J equals 0 rotational quantum number 0, non-rotating, and J equals 1 lowest rotation state. The energy difference between these levels is about 170 Kelvin in temperature units. At 1 Kelvin, thermal energy cannot excite J equals 1 rotation, so essentially all H's molecules reside in the J equals 0 ground state. This rotational ground state population has chemical consequences. The symmetry of H's depends on whether it is in an even or odd rotational state, and whether the nuclear spins are aligned ortho-H's or anti-aligned pair H's. At high temperatures, 3/4 of H's is ortho-parallel spins, odd J, and 1/4 is pair anti-parallel spins, even J. At low temperatures where only J equals 0 is populated, all H's should be pair. The conversion from ortho to pair is slow without a catalyst, but cosmic rays and reactive surfaces facilitate conversion. In the boomerang, the pair-ortho ratio likely favors pair strongly, affecting reactions where spin symmetry matters. Quantum effects also modify the equation of state at low temperatures. The pressure of an ideal classical gas is P equals nKT, where n is number density, K is Boltzmann's constant, and T is temperature. Quantum gases develop additional pressure terms from degeneracy and from zero-point motion. For molecular hydrogen at the boomerang's conditions, these quantum corrections are small, modifying pressure by a few %. But they become crucial in understanding the precise dynamics of the expansion. The cooling process itself has quantum aspects. Adiabatic expansion cools gas as it does work against its own pressure, but the final temperature depends on the heat capacity, which quantum mechanics modifies at low temperatures. Classically, a monatomic gas has heat capacity 3/2 times Boltzmann's constant per particle, 3 translational degrees of freedom, each contributing 1/2 K. A diatomic molecule adds rotational and vibrational degrees of freedom, increasing heat capacity. At low temperatures, vibrational modes freeze out, first requiring thousands of Kelvin to excite, then rotational modes freeze out requiring tens to hundreds of Kelvin, until only translational motion remains. For H's at 1 Kelvin, only translation contributes to heat capacity, and the gas behaves like a monatomic gas thermodynamically despite being molecular. This affects how the temperature drops during expansion, with quantum freezing of rotational degrees of freedom altering the cooling curve. Molecular energy transfer mechanisms change in the quantum regime. Normally, molecules exchange energy through collisions, with rotational and translational energy converting between forms, equilibrating the temperature. At 1 Kelvin with frozen rotational states, collisions primarily transfer translational energy. Inelastic collisions that change rotational states are suppressed because the energy mismatch is too large compared to the collision energy. This suppression affects thermalization timescales and could create non-equilibrium distributions where different molecular species have slightly different temperatures. The lifetime of excited states also changes. Molecules can be excited to higher energy states by absorbing starlight or through cosmic ray impacts. Normally, they relax through collisions, transferring the excess energy to other molecules as heat. In the boomerang's low-density environment, collisions are infrequent, roughly 1 per month for a given molecule, so radiative decay becomes competitive with collisional relaxation. Molecules excited to high rotational or vibrational states may emit infrared photons before colliding, creating a non-thermal radiation field that Webb detected in the nebula's spectrum. Dust grains in the nebula also exhibit quantum behavior. Grains contain billions of atoms, seemingly too large for quantum effects, but at 1 Kelvin, even macroscopic properties become quantized. The vibrational modes of dust grains, acoustic resonances in the solid structure, have quantized energies. The lowest vibrational quanta have energies around 1 Kelvin in temperature units, meaning even the grain vibrations freeze into quantum ground states. This affects how grains absorb and emit radiation, potentially creating discrete absorption or emission features in the infrared spectrum. Another subtle quantum effect involves photon interactions. The boomerang absorbs cosmic microwave background photons at 0.7 to 5 Kelvin and must somehow maintain a temperature lower than the radiation field heating it. This requires that the expansion cooling rate exceeds the CMB heating rate, but quantum mechanics modifies the absorption cross-sections. At 1 Kelvin, molecules can only absorb CMB photons with energies exceeding the energy gaps to accessible excited states. For H's, the lowest rotational transition has an energy corresponding to 85 Kelvin, far above the CMB's peak. Thus H's cannot easily absorb CMB photons, reducing the heating rate below classical estimates. Other molecules with lower-lying rotational levels, like CO, can absorb CMB photons more readily. CO has rotational transitions at energies equivalent to 5 to 10 Kelvin, well matched to the Wien tail of the CMB spectrum. These molecules absorb CMB photons, warming slightly above the H's temperature, then transfer energy to H's through collisions. The balance between CMB heating, adiabatic cooling, and collisional energy transfer determines the final equilibrium temperature, which can be below the CMB temperature during rapid expansion. Understanding these quantum effects is essential for interpreting Webb's observations. The molecular emission lines detected by MIRI arise from quantum transitions between discrete energy levels. The relative intensities of different lines encode the populations of different quantum states, which in turn reveal the temperature, density, and excitation conditions. Classical models fail to predict the observed line ratios. Quantum mechanical models are required to match the data. The detection of complex molecules at 1 Kelvin demonstrates that quantum chemistry allows richer chemical networks than classical chemistry would predict. Reactions proceed through tunneling, driven by cosmic ray ionization, creating a diverse molecular inventory despite extreme cold. The Boomerang Nebula serves as a natural laboratory for quantum chemistry, testing theoretical predictions under conditions in accessible terrestrial laboratories. Webb's observations validate quantum chemical models and reveal where current theory needs refinement, pushing our understanding of how molecules behave at the quantum frontier between chemistry and quantum mechanics. Dying star. At the heart of the Boomerang Nebula lies a dying star, the engine that created this cosmic refrigerator. This star, once a red giant similar to what the Sun will become in 5 billion years, has ejected its outer layers and now transitions toward becoming a white dwarf. A stellar remnant that will cool and fade over trillions of years. Understanding the central star is crucial for understanding the nebula, because the star's evolution dictated when, how, and why the mass ejection occurred, creating the conditions for extreme cooling. The central star of the Boomerang Nebula is difficult to observe directly. Heavy obscuration by dust in the nebula absorbs most of the star's optical and ultraviolet light, making it appear much fainter than its intrinsic luminosity would suggest. Infrared observations penetrate the dust more effectively, and Webb's near-infrared imaging provided the clearest view yet of the central source. The star's estimated luminosity is approximately 2,000 to 4,000 times the Sun's luminosity, though uncertainty remains due to the difficulty in measuring extinction precisely. The star's surface temperature, estimated from its infrared spectrum, is approximately 5,000 to 7,000 Kelvin. This is cooler than the Sun's 5,800 Kelvin, placing the star in the spectral class K or perhaps early M. For a post-asymptotic giant branch post-AGB star, this temperature is low. Most post-AGB stars have temperatures of 10,000 to 30,000 Kelvin or higher, having contracted and heated as they evolve toward white dwarf status. The Boomerang's central star appears to be in an early phase of this evolution, not yet fully contracted. Theoretical models of post-AGB evolution provide context. When a red giant exhausts helium fusion in its core, the inert carbon-oxygen core contracts, releasing gravitational energy that drives further expansion of the envelope. Eventually, the envelope becomes so extended and loosely bound that pulsations or radiation pressure ejects it entirely. The star's exposed core, initially at the photospheric temperature of the red giant 3,000 to 4,000 Kelvin, begins contracting. As it contracts, it heats, eventually reaching 30,000 Kelvin or more when it ionizes the ejected envelope, creating a bright planetary nebula. The Boomerang's central star seems to be caught early in this process. The temperature of 5,000 to 7,000 Kelvin suggests it has only recently emerged from the red giant envelope, having contracted enough to heat above red giant temperatures but not yet reaching the temperatures needed to ionize the nebula. This early phase typically lasts 1,000 to 3,000 years, after which the star heats rapidly as it contracts toward white dwarf dimensions similar to Earth's size and temperatures exceeding 100,000 Kelvin. The star's mass is estimated empirically through models. The core mass of a post-AGB star depends on the progenitor star's initial mass. For stars like the Sun 1 solar mass, the core mass is about 0.6 solar masses. For stars with 2 to 3 solar masses, core masses reach 0.7 to 0.9 solar masses. The Boomerang's progenitor was probably in the 2 to 4 solar mass range based on the nebula's chemical composition, showing S-process element enrichment typical of intermediate mass stars and the energetics of the mass ejection. This suggests the central star's mass is about 0.6 to 0.8 solar masses, though estimates are uncertain. The extreme mass loss rate that created the Boomerang requires explanation. Normal red giant mass loss through winds proceeds at rates around 10 to 7 to 1,000 solar masses per year, driven by radiation pressure on dust grains forming in the cool extended atmosphere. The Boomerang required mass loss at 10 to 3 solar masses per year, roughly 1,000 times faster, sustained for about 1,500 years to eject the 0.1 to 0.3 solar masses observed in the nebula. One hypothesis invokes binary star interactions. If the Boomerang's central star has a companion, gravitational interactions could have enhanced mass loss dramatically. Several mechanisms are possible. In a common envelope phase, the companion star spirals inward through the red giant's extended envelope, transferring orbital energy to the envelope and ejecting it. This produces rapid mass loss on timescales of years to centuries and often creates bipolar outflows due to rotational effects. The final configuration is a binary with much smaller separation than initially, possibly detectable through radial velocity variations or eclipses. Webb's observations have not yet detected a companion, but the central star's faintness and heavy dust obscuration make detection difficult. Future observations with longer integration times and at longer infrared wavelengths might reveal a companion. Alternatively, the companion could be faint, a low-mass main sequence star or white dwarf, and contribute negligibly to the total infrared light. Radial velocity monitoring over months to years could detect periodic variations indicative of orbital motion, providing indirect evidence for a binary. Another explanation involves very late thermal pulses. During the early white dwarf phase, stars can experience brief reignitions of helium fusion in a shell if unburned helium remains. These pulses release enormous energy over short timescales, months to years, inflating the star back to giant dimensions and driving superwinds with mass loss rates exceeding 10 to 3 solar masses per year. The star then contracts again, and the cycle may repeat. Several planetary nebulae show evidence of very late thermal pulses, including Sakurai's object NV4334 SGR Sakurai's object, which brightened dramatically in the 1990s due to a thermal pulse. If the Boomerang resulted from a thermal pulse, the central star would have expanded and cooled during the pulse, ejecting mass rapidly, then contracted afterward. The current cool temperature could reflect the star still recovering from the pulse, having not yet contracted fully. The timescale fits. Thermal pulses occur roughly 1,000 to 3,000 years apart, consistent with the nebula's age. Future observations monitoring the star's temperature and luminosity could detect continued heating, supporting this scenario. A third possibility is an enhanced superwind triggered by the transition from the asymptotic giant branch to the post-AGB phase. Some models suggest that the rapid changes in stellar structure during this transition can drive pulsational instabilities or radiation-driven superwinds. If the star had unusually high mass loss during this transition, lasting perhaps 1,000 years, it could eject the observed nebular mass. This mechanism requires special conditions, possibly related to the star's chemical composition, rotation, or magnetic fields. The bipolar morphology of the Boomerang suggests rotation plays a role. Rapidly rotating stars develop equatorial density enhancements or disks due to centrifugal forces. Mass loss is suppressed in the equatorial plane and enhanced at the poles, creating bipolar outflows. The Boomerang's pronounced hourglass shape is consistent with a rotating star ejecting mass preferentially along the poles. If the star was spun up by accreting material from a binary companion, this could explain both the rapid mass loss binary interaction and the bipolar shape rotation. Magnetic fields could also contribute. Some post-AGB stars show evidence of strong magnetic fields, possibly generated by dynamos in the envelope or preserved from earlier evolutionary phases. Magnetic fields can channel mass loss along field lines, creating jet-like structures. If the boomerang's progenitor had a dipolar magnetic field aligned with the rotation axis, this could focus mass loss into the observed polar lobes while suppressing equatorial ejection. The central star's future evolution is predictable in broad terms. It will continue contracting and heating, reaching 10,000 Kelvin within perhaps 500 years, 30,000 Kelvin within 2,000 to 3,000 years, and eventually exceeding 100,000 Kelvin. As temperature increases, ultraviolet radiation will ionize the ejected nebula, transforming it from a cold molecular cloud into a bright emission nebula glowing in the light of ionized hydrogen, helium, and heavier elements. The boomerang will lose its status as the coldest place in the universe, warming toward the cosmic microwave background temperature and beyond. Simultaneously, the star will stop losing mass. Most AGB stars have weak winds compared to red giants, losing perhaps K-9 solar masses per year, negligible compared to the nebular mass. The rapid mass loss that created the boomerang was a transient phase now ended. The star's current wind, if detected, would be orders of magnitude weaker, having little effect on the nebula's evolution. Eventually, the star will settle onto the white dwarf cooling track. Having exhausted all nuclear fuel, it will shine only by radiating stored thermal energy from its hot interior. Over billions of years, the star will cool from 100,000 Kelvin to 10,000 Kelvin to eventually below 5,000 Kelvin, becoming a black dwarf, a cold dark stellar remnant. The nebula will have long since dispersed, mixed into the interstellar medium, its atoms recycled into future stars and planets. The boomerang's central star represents a critical phase in stellar evolution, the transition from red giant to white dwarf, a transition all sun-like stars eventually experience. The star's peculiarities, its rapid mass loss, bipolar morphology, and current cool temperature reflect the diversity of evolutionary pathways stars can follow. Not all dying stars create boomerang-like nebulae. Most produce more typical planetary nebulae with spherical or elliptical shapes and warmer temperatures. Understanding what made the boomerang's central star special reveals the range of behaviors possible during stellar death and the complex interplay of mass loss, rotation, binarity, and nuclear burning that govern a star's final transformation. Molecular menagerie. The molecular complexity Webb detected in the Boomerang Nebula is staggering. Over 80 different molecular species, from simple diatomic molecules to complex organics with dozens of atoms, coexist in this frozen environment, actively forming, destroying, and transforming through chemical networks that operate at temperatures where classical chemistry should be frozen solid. Understanding this molecular menagerie requires examining the specific molecules detected, how they form, and what their presence reveals about the conditions and processes in the nebula. Carbon monoxide (CO) is the second most abundant molecule after H's and the primary coolant for the nebula. Co-forms efficiently in stellar atmospheres when carbon and oxygen combine at temperatures around 2,000 to 3,000 Kelvin. Once formed, CO is extremely stable, requiring ultraviolet radiation or temperatures exceeding 4,000 Kelvin to dissociate. In the boomerang, CO survives intact from formation in the red giant atmosphere through ejection and cooling. The molecule's rotational transitions emit infrared photons that carry away energy, contributing to the nebula's cooling. The J=1 to J=0 rotational transition at 2.6 mm wavelength is particularly important for cooling at temperatures around 5 to 10 Kelvin. Water, how is abundant, formed both in the stellar atmosphere and through gas phase chemistry in the nebula. In oxygen-rich environments, more oxygen than carbon, water is the dominant oxygen-bearing molecule after CO. Formation occurs through reactions like O plus H's gives O plus H, followed by O plus H's gives H plus H. These reactions have small or negligible activation barriers and proceed through hydrogen atom abstraction, which can occur via quantum tunneling at low temperatures. Webb detected water ice on dust grains in the cooler regions, where H molecules stick to grain surfaces and freeze, creating ice mantles. Ammonia NH, the nitrogen equivalent of water, forms through nitrogen chemistry. Molecular nitrogen N is very stable and difficult to break apart, so nitrogen chemistry in molecular clouds typically begins with atomic nitrogen or with NH radicals formed through cosmic ray chemistry. The reaction N plus H gives NH plus H requires tunneling at low temperatures but can proceed slowly. Subsequent hydrogenation reactions NH plus H's gives NH plus H and NH plus H's gives NH plus H build ammonia. The detection of ammonia in the boomerang confirms active nitrogen chemistry despite the extreme cold. Formaldehyde HCO is a simple organic molecule containing carbon, hydrogen, and oxygen in a structure where carbon bonds to two hydrogens and one oxygen. Formaldehyde forms on cold dust grain surfaces when carbon monoxide molecules adsorbed on the grain are hydrogenated by hydrogen atoms landing on the grain. CO plus H gives HCO, then HCO plus H gives HCO. At the nebula's temperature, molecules stick efficiently to grain surfaces and can diffuse slowly across the surface, encountering other molecules and reacting. When cosmic rays heat a grain briefly, the formaldehyde can evaporate into the gas phase, where Webb detects it. Methanol CHO is more complex, containing a methyl group J bonded to a hydroxyl group O. Methanol likely forms on grain surfaces through further hydrogenation of formaldehyde. HCO plus H gives CHO, then CHO plus H gives CH. Methanol is considered a relatively complex molecule, requiring multiple steps to assemble. Its detection indicates grain surface chemistry proceeds efficiently in the boomerang, with hydrogen atoms abundant enough to hydrogenate adsorbed CO and HCO sequentially. Methanol's presence is also interesting because it is considered a potential biosignature in exoplanet atmospheres when found in conjunction with other organic molecules. Hydrogen cyanide HCN is a carbon-nitrogen molecule fundamental to prebiotic chemistry on Earth. HCN forms through reactions between nitrogen atoms, or radicals, and hydrocarbons. One pathway is CN plus H's gives HCN plus H, where CN radicals come from dissociation of nitrogen-bearing molecules by cosmic rays or ultraviolet photons. HCN is interesting because in aqueous environments, liquid water, it polymerizes to form adenine, one of the nucleobases in DNA. While the boomerang lacks liquid water, the presence of HCN as a building block is noteworthy. Acetylene CH is a simple hydrocarbon, two carbon atoms bonded together with hydrogen atoms. Acetylene forms through carbon chemistry in the nebula, likely starting from atomic carbon reacting with hydrocarbons. The sequence might be C plus H's gives CH plus H tunneling reaction, CH plus H's gives CH plus H, then carbon insertion reactions building longer chains. Acetylene is also a building block for more complex polycyclic aromatic hydrocarbons PAHs, serving as a precursor in the stepwise assembly of aromatic rings. PAHs are large molecules consisting of fused benzene rings, flat structures with dozens to hundreds of atoms. The smallest PAH is naphthalene to benzene rings, CCH, but PAHs in space often range to C Dutch or larger. Webb's detection of PAH emission features in the boomerang spectrum was unexpected because PAHs are thought to form in hot environments like carbon-rich stellar outflows or shocked regions. Their presence suggests either they formed during ejection when the gas was hotter, or they are assembling from small hydrocarbons through low-temperature chemistry. The PAH formation mechanism at low temperatures is speculative but may involve radical additions. Acetylene can add to aromatic radicals through reactions without activation barriers, growing the aromatic structure. Cosmic rays create radicals by ionizing molecules and dissociating them, and these radicals drive further chemistry. Alternatively, PAHs might form on grain surfaces where molecules can encounter each other more frequently than in the gas phase, assembling through surface reactions before evaporating into the gas. Several sulfur-bearing molecules were detected, including hydrogen sulfide H's and sulfur dioxide SO. Sulfur chemistry parallels oxygen chemistry in some ways, with H's being the sulfur analog of water. Sulfur is less abundant than oxygen, about 1/50th as abundant by number in solar composition material, so sulfur molecules are correspondingly rarer. The detection of multiple sulfur species indicates that despite low abundance, sulfur participates actively in the chemical network. Silicon-bearing molecules like silicon monoxide SiO were also found. Silicon combines with oxygen to form SiO in stellar atmospheres, similar to carbon monoxide. SiO is important because it is the gas phase precursor to silicate dust grains. When SiO molecules collide and polymerize, they form small clusters that grow into solid grains of silicate minerals, primarily magnesium and iron silicates. The presence of SiO alongside dust grains traces the process by which gas condenses into solid material. Complex organic molecules (COMs), defined as molecules with 6 or more atoms containing carbon, make up a significant fraction of the detected species. Examples include acetaldehyde CHO, formic acid HCOH, and dimethyl ether CHOCH. These molecules are chemically interesting because they contain multiple functional groups, carbonyl groups, alcohols, esters that in biological chemistry play crucial roles. While the boomerang is far from biological, the presence of these functional groups demonstrates that space chemistry can produce structural motifs common in biochemistry. The chemical network linking all these molecules is complex, with thousands of reactions proceeding simultaneously at various rates. Reaction kinetics at 1 Kelvin are dominated by processes that do not require activation energy, ion molecule reactions, radical molecule reactions, and quantum tunneling reactions. Cosmic rays drive the network by creating ions and radicals. Starlight, though faint in the nebula's outer regions, photodissociates some molecules and drives photochemistry. Grain surface reactions contribute molecules that evaporate or are sputtered into the gas. The molecular abundance is relative to hydrogen reveal the efficiency of different chemical pathways. CO is abundant, roughly 1 CO molecule per 10,000 H, consistent with carbon and oxygen combining efficiently. Water is similarly abundant. Ammonia is less abundant, around 1 per 100,000 H, reflecting nitrogen's lower abundance and the difficulty of breaking it. Complex organics are trace species, abundances around 1 per billion H's, yet their presence at detectable levels is significant. The isotopic ratios in molecules provide additional information. Webb spectroscopy detected isotopologues, molecules with different isotopes. For example, both 1:CO and 1:3CO were detected, allowing measurement of the 1:C 1:3C ratio. This ratio traces nuclear processing in the central star. Stars produce 1,3C through CNO cycle fusion, and convection can dredge 103 to the surface, enriching the ejected material. The measured ratio in the boomerang is somewhat lower than solar, indicating enrichment in 1,3C, consistent with moderate dredge-up during the asymptotic giant branch phase. Deuterium-bearing molecules like deuterated water HDO were searched for but not conclusively detected. Deuterium, the heavy isotope of hydrogen, is rare DH ratio about to 1,000 in the solar system. And its enrichment in molecules depends on low-temperature fractionation reactions that favor deuterium incorporation at very low temperatures. The non-detection suggests either deuterium fractionation has not proceeded extensively in the boomerang, or the abundances are below Webb's detection limits. Structural secrets beyond the molecular chemistry. Webb's high-resolution imaging revealed the Boomerang Nebula's structure in unprecedented detail, uncovering features that trace the history of mass ejection and the hydrodynamic processes shaping the nebula's evolution. The structure is not simply a smooth, expanding bubble but a complex interplay of lobes, shells, filaments, and knots, each telling part of the story of how this dying star shed its envelope. The overall morphology is bipolar, with two prominent lobes extending north and south from the central star. Each lobe has a roughly conical shape, opening wider with increasing distance from the star, suggesting a collimated outflow that expands as it propagates. The lobes are not perfectly symmetric. The northern lobe extends slightly farther and appears brighter in Webb's infrared images, while the southern lobe shows more substructure and filamentary patterns. This asymmetry could reflect differences in the mass ejection process between the two poles or interaction with an asymmetric interstellar medium. The waist connecting the two lobes is narrow, only about 0.1 light-years in diameter compared to the full extent of 1 light-year. This narrow waist suggests that mass ejection was highly collimated, with very little material escaping in the equatorial plane. Models of bipolar planetary nebulae invoke dense equatorial disks or toroids that block mass loss in the equator and channel it toward the poles. The Boomerang's pronounced hourglass shape is consistent with such a model, where a rotating star with a dense equatorial structure confines the outflow to a narrow solid angle around each pole. Webb's images show multiple nested shells within the lobes, visible as concentric arc-like features at different radii. These shells likely represent discrete episodes of enhanced mass loss separated in time. If the central star underwent pulsations or thermal pulses that episodically increased mass loss, each pulse would create a shell of material that expands outward. Later pulses create shells inside earlier ones, producing the nested structure. The spacing between shells, approximately 0.05 light-years, corresponds to ejection events separated by 100 to 200 years given the expansion velocity. Filamentary structures within the lobes are among the most striking features revealed by Webb. These filaments are thin, thread-like features only a few hundred O wide but extending for thousands of O along the lobe. They appear denser and slightly warmer than the surrounding gas. The filaments likely result from hydrodynamic instabilities in the expanding flow. As fast-moving gas from the central star catches up with slower material ejected earlier, Rayleigh-Taylor instabilities develop at the interface, creating finger-like structures that penetrate into the slower material. Alternatively, filaments could trace magnetic field lines. If the central star has a magnetic field lines frozen into the outflowing gas would organize the material along their geometry. Observations of linear polarization in dust emission could test this hypothesis by revealing whether dust grains align with magnetic fields. Webb does not have polarimetric capabilities, but future polarization studies with ALMA or other facilities could determine if magnetic fields play a role in the boomerang structure. Knots are compact clumps within the lobes, visible as bright spots in Webb's images. These knots are denser than the surrounding gas, with densities perhaps 10 to 100 times higher, and slightly warmer, around 2 to 3 Kelvin compared to the 1 Kelvin background. The knot's survival in the fast-moving flow suggests they are dense enough to resist disruption by shear forces and ram pressure. Their formation mechanism is uncertain but may involve instabilities that fragment the outflow, creating clumps that then cool and compress into long-lived dense structures. Some knots show proper motion, displacement across the sky in images taken years apart. Hubble observed the boomerang in 1998 and again in 2005 and 2012, allowing measurement of knot motions. Several knots moved radially outward at speeds consistent with the overall expansion velocity, confirming they are embedded in the outflow rather than stationary structures. The detection of proper motion also confirmed the expansion velocity measured spectroscopically, providing independent validation. The transition between the cold outer lobes and the warmer inner regions shows a sharp gradient. Webb's temperature maps, derived from molecular line ratios and dust continuum emission, show temperature rising steeply within a narrow zone about 0.05 light-years from the star. This sharp transition indicates the heating mechanism, likely photoheating by starlight, becomes suddenly effective at this radius, possibly because dust optical depth drops or because the ionization fraction increases, changing the gas's thermal properties. Webb also detected evidence of shock fronts at the leading edge of the lobes, where the expanding nebula encounters the surrounding interstellar medium. The interstellar medium in this region has a density around 100 to 1,000 particles per cubic centimeter, typical for the galactic disk. The boomerang's lobes, expanding at 164 kilometers per second, create a bow shock as they plow into this ambient material. The shock heats gas to temperatures around 100 Kelvin, detectable through specific molecular emission lines that trace shock-heated gas. The central star's immediate surroundings show a different structure. Within about 1,000 astronomical units of the star, Webb detected a compact, warm region with temperatures exceeding 100 Kelvin, likely heated directly by starlight. This region shows emission from warm molecules like water vapor and possibly atomic emission from singly ionized species. As the star continues heating on its way to white dwarf status, this warm region will expand, eventually ionizing the entire nebula. Three-dimensional structure is difficult to infer from images alone since we observe only a two-dimensional projection on the sky. However, spectroscopy provides the third dimension through Doppler velocities. The northern lobe shows redshifted emission, indicating it is moving away from us, while the southern lobe is blue-shifted, moving toward us. This confirms the lobes are oriented nearly perpendicular to our line of sight, explaining the bow-tie appearance. The velocity difference between the lobes, about 330 km per second, each lobe moving at plus or minus 165 km per second, matches the expansion velocity measured radially. Detailed velocity maps reveal that the expansion is not uniform. The outer edges of the lobes move slightly faster than the inner regions, indicating ongoing acceleration. This acceleration likely results from radiation pressure or from fast wind from the central star pushing on the previously ejected material. The acceleration profile constrains the mass loss history, showing that the star has reduced its mass loss rate over time. Early ejected material, now in the outer lobes, experienced less subsequent acceleration, while more recently ejected material closer to the star is being pushed faster. Another structural feature is the faint halo detected around the lobes in the deepest Webb images. This halo extends to nearly twice the radius of the bright lobes, about 1.5 light-years from the star, and has much lower surface brightness. The halo likely represents material ejected earlier during the red giant phase, before the rapid mass loss that created the main lobes. This earlier material expanded more slowly, around 20 to 30 km per second, typical of red giant winds, and has now been overtaken by the faster bipolar outflow. The halo's detection shows that the boomerang's mass loss history includes multiple phases with different ejection velocities and morphologies. The three-dimensional structure can be modeled using radiative transfer and hydrodynamic simulations. Astronomers input assumptions about mass distribution, velocity structure, and temperature into codes that calculate how the nebula would appear at various wavelengths. Comparing simulated images and spectra to Webb's observations constrains the model parameters. Recent models suggest the boomerang is best described as a hollow bipolar cone or cavity carved out of a roughly spherical, slowly expanding halo, with the cavity walls dense and cold while the interior is more diffuse. The structure also reveals information about the nebula's age and future evolution. The outermost material in the lobes is approximately 0.5 light-years from the star. At an expansion velocity of 164 km per second, this material has been traveling for about 1,800 years. This provides an independent estimate of the nebula's age, consistent with the 1,500-year age estimated from other methods. In the future, the lobes will continue expanding, gradually slowing as they sweep up interstellar material and as the driving pressure from the central star diminishes. Within 10,000 years, the boomerang will no longer be recognizable in its current form. The central star will have heated enough to ionize the nebula, transforming it into a bright emission nebula with temperatures of 10,000 Kelvin, orders of magnitude warmer than today. The delicate cold structure's Webb image will be destroyed, evaporated by ionizing radiation, and heated by shocks. The nebula will resemble more typical planetary nebulae like the Ring Nebula or Helix Nebula, glowing shells of ionized gas illuminated by a hot white dwarf. The boomerang's reign as the coldest place in the universe will end, a transient phase in the transformation of a dying star. Life's building blocks. The detection of complex organic molecules in the Boomerang Nebula raises profound questions about the ubiquity of life's chemical precursors in the universe. While the nebula is far from habitable, the molecules Webb found include many considered essential for life as we know it: carbon-rich organics forming structural frameworks, nitrogen compounds that could participate in amino acid synthesis, and functional groups that in biological systems facilitate chemical reactivity. Understanding what these molecules mean for astrobiology requires examining which molecules are biologically relevant, how they form in space, and what pathways might lead from interstellar chemistry to life. Carbon is the foundation of biological chemistry due to its ability to form stable bonds with itself and many other elements, creating molecular complexity. Carbon forms for covalent bonds, allowing construction of chains, branches, and rings of arbitrary complexity. The boomerang contains carbon in multiple forms: atomic carbon, carbon monoxide, simple hydrocarbons like acetylene, and complex organics. The progression from simple to complex carbon chemistry visible in the nebula mirrors, in some ways, the chemical evolution that must occur for life to emerge. The simplest organic molecules detected methane CH, acetylene CH, ethylene CH are pure hydrocarbons, carbon and hydrogen only. These molecules are building blocks for more complex chemistry but are not themselves biologically functional. On Earth, methane is produced by biological and geological processes, but in space, it forms through simple hydrogenation of carbon atoms or ions. The detection of methane in the Boomerang reflects basic carbon chemistry, not biological activity. More complex organics containing oxygen or nitrogen functional groups are more biologically interesting. Formaldehyde HCO is a precursor to sugars. In the foremost reaction, formaldehyde molecules combine under basic conditions to form sugars including ribose, a component of RNA. While the Boomerang lacks the liquid water environment needed for the foremost reaction, the presence of formaldehyde shows that this sugar precursor forms readily in space. Meteorites containing formaldehyde could deliver it to planets where liquid water could drive further chemistry. Methanol CH is both a simple organic solvent and a reactant in many organic synthesis reactions. In prebiotic chemistry scenarios, methanol reacts with ammonia and hydrogen cyanide to form amino acid precursors. The coexistence of methanol, ammonia, and HCN in the Boomerang demonstrates that the necessary ingredients are spatially associated, though the cold temperature prevents them from reacting. Delivered to a warmer environment, these molecules could participate in prebiotic synthesis. Hydrogen cyanide is perhaps the most important molecule from an astrobiological perspective. HCN polymerizes to form adenine, one of the 5 nucleobases in DNA and RNA. The polymerization occurs when HCN solutions are heated or exposed to ultraviolet light, producing first dimers and trimers of HCN, then eventually adenine and other heterocyclic compounds. HCN also reacts with formaldehyde and ammonia to form amino acids through the Strecker synthesis. The detection of HCN in the Boomerang, and in many other interstellar environments, suggests this crucial molecule is widespread. Ammonia is essential for nitrogen incorporation into biological molecules. Amino acids contain nitrogen in amino groups NH, and nucleobases contain nitrogen in their ring structures. Ammonia is the primary nitrogen source in many prebiotic synthesis reactions. Its formation in the Boomerang through nitrogen chemistry shows that even in extreme cold, nitrogen can be converted from inert and into reactive forms capable of forming biological molecules. Polycyclic aromatic hydrocarbons are intriguing because their flat, rigid structures can stack and interact in ways similar to nucleobases in DNA. Some origin of life theories propose that PAs served as primitive scaffolds for information storage before RNA emerged, with sequences of different PAs encoding information analogous to nucleotide sequences. While speculative, the widespread occurrence of PAs in space, including in the Boomerang, shows that complex carbon structures form naturally and could have been present during early Earth's prebiotic chemistry. The molecules detected also include species relevant to metabolism. Formic acid HCOH is the simplest carboxylic acid and is involved in some metabolic pathways. Acetaldehyde CHO is an intermediate in fermentation and other metabolic processes. While these molecules' roles in modern biochemistry do not necessarily imply they were important in life's origin, their presence demonstrates that chemical diversity extends to functional groups central to biology. The question arises, could life exist in the Boomerang Nebula itself? The answer is almost certainly no. Life as we know it requires liquid water, energy sources, and temperatures compatible with complex chemistry. The Boomerang's temperature of 1 Kelvin is far too cold for liquid water, which freezes at 273 Kelvin. Even the most cold-adapted organisms on Earth require temperatures above about 250 Kelvin. The nebula has no obvious energy sources beyond faint starlight and cosmic rays, insufficient to drive the sustained far-from-equilibrium chemistry that life requires. However, the nebula is not the final destination for its molecules. The Boomerang will eventually disperse, mixing into the interstellar medium over hundreds of thousands of years. The molecules will become part of giant molecular clouds, the dense regions where stars and planets form. When new stars ignite, warming their surroundings, The molecules from the boomerang and countless other sources will vaporize from dust grains and participate in the chemistry of protoplanetary disks, regions where planets coalesce. Some of these molecules will be incorporated into comets and asteroids during planet formation. Comets, in particular, preserve pristine material from the outer protoplanetary disk, including organic molecules. When comets and asteroids collide with young planets during late accretion phases, they deliver water and organic compounds. Earth received a significant fraction of its water and perhaps a substantial inventory of organic molecules through such impacts during the late heavy bombardment approximately 4 billion years ago. The organic molecules delivered to Earth included many of the species Webb detected in the boomerang. Analysis of meteorites, particularly carbonaceous chondrites like the Murchison meteorite, reveals amino acids, nucleobases, sugars, and amphiphilid compounds that self-assemble into membrane-like structures. These molecules, likely formed in space through low-temperature chemistry similar to that in the boomerang, were incorporated into the meteorite's parent body and eventually delivered to Earth. The ubiquity of complex organics in space changes how we think about life's origin. Early theories assumed prebiotic chemistry began on Earth with simple molecules like methane and ammonia, which then reacted in the atmosphere or oceans to form complex organics. The famous Miller-Urey experiment in 1953 demonstrated that electrical discharges through simple gas mixtures produce amino acids and other organics. But we now know that space chemistry already produces substantial complexity before molecules reach planets. This does not eliminate the need for terrestrial prebiotic chemistry, but it changes the starting point, rather than beginning with simple gases. Earth's prebiotic chemistry likely started with a rich inventory of space-delivered organics. Amino acids, nucleobases, sugars, amphiphiles. The challenge shifts from explaining how to make these molecules to explaining how to organize them into self-replicating, metabolizing systems. The transition from chemistry to biology. The boomerang's chemistry also informs the search for life beyond Earth. Exoplanet atmospheres are analyzed for biosignatures, molecules or combinations of molecules indicating biological activity. Oxygen, methane, and phosphine are considered biosignatures when found together because abiotic processes rarely produce such combinations. But identifying biosignatures requires understanding background abiotic chemistry. The rich organic chemistry in the boomerang and other space environments shows that complex organics form readily without biology, so their detection in exoplanet atmospheres is not necessarily a biosignature. Instead, biosignatures might be thermodynamic disequilibria that require sustained energy input to maintain, suggesting metabolic activity, or they might be specific stereoisomers. Molecules that exist in mirror-image forms where biology preferentially produces one form. Earth, life uses only left-handed amino acids and right-handed sugars. Asymmetry-breaking choice that could flag biological origin if detected remotely. The boomerang's molecular inventory also raises questions about alternative biochemistries. Life on Earth is carbon-based, using water as a solvent and operating near 300 Kelvin. But could life exist with different chemistry at different temperatures? Some speculate about methane-based life at cryogenic temperatures, using liquid methane as a solvent instead of water. Saturn's moon Titan has liquid methane lakes and a rich atmospheric organic chemistry, making it a test case. However, chemical reaction rates at Titan's 94 Kelvin surface are far slower than in water at 300 Kelvin, potentially making metabolism prohibitively slow. Life at 1 Kelvin is even more implausible. Reaction rates become vanishingly small, and available energy is minimal, while quantum tunneling allows some chemistry. The rates are far too slow for complex metabolic networks. Replication and evolution require many generations within reasonable timescales, and at 1 Kelvin, timescales stretch to geological epochs for processes that on Earth take seconds or minutes. Yet the boomerang teaches that chemistry is active even at extreme cold, driven by quantum tunneling and cosmic rays. This suggests chemical complexity can arise across a broader range of conditions than previously thought. While life seems unlikely at 1 Kelvin, the lower temperature limit for life remains uncertain. Could life exist at 200 Kelvin? 150 Kelvin? How slow can metabolism be while still constituting life? These questions remain open, and understanding chemistry at the boomerang's temperature illuminates the boundaries.